Okay, so now we're going to look at addition properties. So the first one we're going to talk about is closure. And so here we're going to see some of the vocabulary that we used when we were talking about sets. So if A and B are in a set, so if they're elements of a set, the closure property holds if A and B, the sum, is also in the set, is also an element of the set. So for example, if we are dealing with the set of integers, so integers are positive and negative numbers, no fractions, no decimals. So if I were to take any two integers, let's say I took 8 and negative 12. 8 is an element of the integer set, negative 12 is an element of the integer set. So if there is closure, then what that means is that the sum would also be an integer. Well, that is the case. So if that's true for any two integers I pick, right, so no matter which two integers I pick, if the answer is also an integer, then it's considered closed for integers. Now, it's really difficult to prove that it's true for everything because you would have to show every single case. So what we want to do is, can we come up with any example where if I take two integers and add them together, I don't get an integer? Is there any way to take any two numbers, negative 15 plus negative 23, and if I add those together, is my answer ever not an integer? Well, I'm thinking really hard. It's like, can I take two integer values, no fractions, no decimals, and when I add them, get something that is a fraction or a decimal? I'm thinking no. So addition is closed under integers. That's kind of the way we say it. It's closed under the set for integers. Okay? So let's look at another set. Let's say we were only looking at odd numbers, odd positives. Okay, so that's where I'm going to grab my first two values. So if I grab any two odd positive numbers, 5 and 11. Okay, both of these are odd and positive, so they both belong to this set. Now when I add them together, 5 plus 11 is, oh wait a minute, it's 16. Okay, well that's a positive, but it's not odd. So my answer is not part of the set that I started with. So it would not be considered closed. So closure for addition does not hold for odd numbers because my answer is not part of my original set. Okay? So closure worked for, so it was a yes, I shouldn't have written everything on the board yet. Yes for integers, no for odd. Okay, let's try something else. What if we had even integers? Let's try that. So let's say we started with even integers. If I pick any two even integers, 14 and 28, and I add them together, I get 42. Okay, that's even. What if I make one of them negative? Negative 16 and 20. Nope, I still get an even. All right, let's try one more. What if we went 8 and 92? Yep, still even. So I'm not coming up with any examples where if I take two even numbers, I get something that's not even. So this is looking like it's closed. So regular integers are closed under addition. Even integers are closed under addition. Let's try one more. Okay, so what if my set is only the numbers 0 and 1? Okay. Well, if I take 0 plus 1, those are both obviously in here, I get 1, which is also in here. Well, what if I decide to use 0 twice? What if I go 0 plus 0? Well, that's 0, and that's part of it here, so that seems to be working. So far, we're closed. Well, there's one more example we should look at, and that's the 1 plus 1. If I take 1 plus 1, they're both in the set that I started with, I get 2. Well, that's not here. So the set 0, 1 would not be closed under addition, because it is possible to take an element of that set and add it and not get an answer. So it's okay that I used the same element twice. That's allowed. But what's not okay is that the answer I got was not in my original set. So that's the idea of closure, is that whatever group you started with, your answer has to be in that group. Okay? All right, so that's closure. The identity property would mean that I need to know, is there some value that if I add a number to it, I just get back what I started with? So is there some value that no matter what I add to it, my answer is just where I started again? And the answer is yes, and that would be 0. So this would be considered the identity element for addition. Because again, the idea of an identity is that whatever you start with, that's what you end up with. And the only way that can happen is if we added 0 to it. Okay? And there's only one identity element for addition. There's not another number that also does that. Okay? So that is unique. All right, so closure, identity. Now we're going to talk about two that that allow us not only to maybe do manipulations with numbers, but they allow us to do some nice mental math techniques. So the first one's commutative property. And the idea of the commutative property deals with the order of the numbers that you're adding. So if I have, for example, 6 plus 8, my answer is 14. And if I were to switch the order and go 8 plus 6, well, remember, think about what addition is doing. It's taking a set of elements that have 6 in it, or a set that has 6 elements in it, and another set that has 8 elements, and it's bringing them together and it's making one big group. So you've got 6 here, and over here you have 8. And now I'm going to put them into one set. That's what addition means. I'm going to take these two sets and I'm going to create their union. And so when I create their union, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 elements. Well, if I were to switch that around and I were to grab the 8 of them first and then put the 6 with them, when I'm done, I still have the same total number of elements. I still have the same union. It didn't matter which of these numbers I started with. I still received the same result. And that's what the commutative property is formalizing. It's saying, hey, when we add, it doesn't matter the order that we add in. Order does not matter. So if I take A plus B, I will get the same answer as B plus A. Okay? So I kind of think about it like when you commute, whether you're going from home to school or whether you're going from school to home, it's the same distance. It didn't matter which order you did the trip. You were covering the same distance. Not necessarily the same time, that's a different argument. But as far as distance goes, it's the same distance. So commutative, the order doesn't matter. Okay? It doesn't matter which you do first. And then the next property has to do with grouping. So again, let's think about it in terms of 3 sets. So let's say I had in this set 3 stars. And over here I had 4 dots. And then over here I had something easy to draw. Let's go just pluses. Okay. So I told you just a second ago, the idea of addition is I take what's in the different sets and I group them and I find their union. So if here I decided to group those two together first and I wanted to find the union of those two sets, I would have 3 stars and 4 dots. And then I would add to that these pluses. And so in the end, I would have all of this in my set. Well, what if I decided instead that I wanted to group these two together first? Well, in that case, I would have had 4 dots and 5 pluses. And to this mix, I would have added the 3 stars. Well, and I end up with the same things in both sets. So it didn't matter which two I grouped together first. I still, in the end, had the same outcome. So let's do that with some numbers, and then we'll do it with some variables. So let's say we had 6 plus 5 plus 9. Okay? Well, 6 plus 5 is 11. I'm going to do parentheses first because order of operations tells me to do that. Plus 9. So 11 plus 9 is 20. Now over here, if I had switched that grouping order, notice the numbers stay exactly the same order. The numbers don't switch. What switches is which do I pair up together first. So if I pair the 5 and the 9 together first, I get 14. And then when I put that with the 6, well, 6 plus 14 is 20. So again, it didn't matter which I grouped together first. I ended up with the same result. That's what the associative property says. With addition, if I take A plus B plus C and group the first two together and then add this third one, I will get the same answer as if I grouped these together and then added the first one. The result does not change. Okay, that's the associative property. Now, where is that an advantage? Lots of places, but one of them has to do with when we're trying to maybe do some mental math, or we're trying to find ways to do some calculations a little bit faster. So let's say you had 17 plus 14 plus 13, and I was supposed to add all those together without a calculator. Well, what I notice is 7 and 3 group together really nicely because they would add up to 10. And so when numbers group together nicely, like they end in a 0, or maybe they're 25s or something like that, we consider those compatible numbers because they're quick and they're easy to do in our head. So if I grouped those together first, this calculation would be easier to do. So what I'm going to do is I'm going to switch the order. I'm going to go 17 plus 13 plus 14. So I'm going to use the commutative property to switch the order. And now these two compatible numbers are next to each other, and I can go, oh look, 17 plus 13, oh that's 30. Well, 30 plus 14, oh that's super easy to do in my head. 30 plus 14, that's 44. All right, so I look for numbers maybe that are easier to add together, put those two together first, and then, using the commutative property, and then get my sum. So what if you had something like 82 plus 97 plus 18? So again, I'm looking at that and I'm going, oh man, I got to do all this in my head. I got to go 82 plus 97, get that answer, and then add 18 to it? Well, wait a second. 82 and 18. Hey, those are pretty compatible numbers because I know that those add to 100, right? 2 and 8, that's a grouping of 10. Wow, and then actually that's a grouping of 100 when I put them together. That I can do. So I'm going to go 82 plus 18. I'm going to use the commutative property to switch the order. And now I'm going to use compatible numbers. to get my answer. 82 plus 18 is 100, plus 97. My answer is 197. Okay, so again, the idea behind compatible numbers is we're trying to make these calculations fast. And so if we look for things that we can group together that we know a total for quickly, and they end up being nice answers, then we can get a quick result. All right, let's look at another example.